right now, beneath the streets of Boston, hundreds of thousands of people are just, swiping pieces of plastic against glass readers.
Yeah, it's happening constantly.
Right, exactly. And in a fraction of a second, this sprawling, completely invisible brain has to figure out, well, who they are, how much money they have, and where they're going.
And it has to do all of that without a single typo. Millions of times a day.
Millions. It's wild. So today we are looking at how that brain is actually built. Welcome to the deep dive. Our mission for this one is to really explore how you, meaning, the engineers, transform the messy, chaotic reality of the physical world into clean, structured digital information.
It is, it's a monumental translation process.
Yeah.
Honestly, we take it totally for granted that a physical action like just walking through a turnstile instantly and flawlessly updates this massive digital ledger. But building the architecture to actually support that, that is a complex engineering feat.
It really is. And to understand how it's done, we are pulling from a pretty phenomenal stack of materials today. We've got lecture notes, technical diagrams, and some really amazing historical visuals from a CS50 course that focuses on SQL and database design.
Yeah, those CS50 materials are fantastic.
They really are. But the lens these sources use to teach database architecture, it isn't just, abstract code. It revolves around this legendary local story, the story of Charlie.
Right, which stems from an old folk song. And that song actually inspired the modern transit card used by the MBTA in Boston, the Charlie card.
I love that the sources quote the song directly, too, for those of you who maybe haven't heard it. It goes, Charlie handed in his dime at the Kendall Square station, and he changed for Jamaica Plain. When he got there, the conductor told him one more nickel. Charlie couldn't get off of that train.
A terrible feat for Charlie, honestly.
Just stuck forever.
But it's an absolute goldmine for us because tracking riders like Charlie, along with, hypothetical commuters like Alice and Bob across the Boston transit system, is just the absolute perfect framework for understanding database design.
Because transit is just inherently messy.
Exactly. People add funds, they change routes, they miss trains. It's chaos.
So let's start at the absolute bottom. The sources show us the most primitive way you could possibly record this transit information. It's just a raw data log. And when you look at it, it reads like a robot's diary.
That is a great way to put it.
It literally says, Charlie Kendall, MIT, enter 10-5, meaning his fare was 10, his balance is 5. And then the next line down says, Charlie Jamaica, plane exit 5, Oreo.
Just completely flat.
Yeah, and then we see other riders too. Alice Harvard, enter 10-20. Alice Park Street, exit 515. Then Bob. Bob Alewife, enter 10:30. It is literally just line after line of flat text.
What's fascinating here is just the sheer brute force nature of this approach. This is what we call unnormalized data.
Unnormal.
Right. The system is just blindingly repeating the same information over and over again. Every single time Charlie takes a train, it writes out his full name. Every time someone enters a station, it logs the full name of the station, the action, the fare amount. That's exhausting just looking at it.
Okay, let's unpack this for a second. Because for anyone listening who, works with standard spreadsheets all day, this might just look like a normal day at the office. You have your columns, you have your rows.
That looks familiar.
But functionally, this is a disaster waiting to happen.
Yeah.
Keeping a flat data log like this is it's like writing down your best friend's full legal name, their exact eye color, and their physical home address every single time you send them a text message.
Oh, wow.
Like, hey, Jonathan Edward Smith, Blue Eyes, 123 Main Street, want to get pizza? It's completely redundant and practically begging for typos.
That analogy is spot on. And the redundancy is really just the first symptom of the underlying disease here. The real danger of a flat database is what happens when the real world changes.
Right, because the world never stays the same.
Exactly. Say the MBTA decides to rename the Kendall MIT station to just Kendall. In a flat database, you have to hunt down every single historical instance of that station in a log of billions of rows. You literally have to update it line by line.
Wait, but can't you just use a global find and replace command? Just search Kendall MIT and hit swap.
You could try, but find and replace is a human safety net. It's not a systemic guarantee. What if one entry was misspelled as Kendall with just one L, like 5 years ago?
Oh man, your search just completely misses it.
Exactly, and now your database officially thinks there are 2 separate physical stations in Boston. A machine needs guaranteed unbreakable structure. It absolutely cannot rely on human vigilance to maintain its integrity.
Okay, so we have to move from just passively recording text to actually mapping the physical world.
We do. And that mapping process is done using entity relationship diagrams, or ER diagrams. Before you write a single line of SQL code, you have to conceptually isolate different ideas.
The source material uses a classic literary example to explain this, right?
Yeah, it does. So instead of a giant flat list of books, you break the world into entities. You have an author, a publisher, a translator.
Hmm.
And they connect via relationships. An author wrote a book, a publisher published a book. The book has an independent relationship to a rating. You're essentially building boundaries around concepts.
This connects so beautifully to one of the historical images provided in the sources. There's this incredible black and white photograph from November 2nd, 1896.
Oh, the subway construction photo.
Yes. It shows the physical construction of Section 5 of the Tremont Street subway in Boston, and you see these men literally digging deep trenches in the dirt. They're putting up heavy timber to shore up the walls, physically routing where the early streetcars will eventually pull into Park Street Station.
It's such a powerful visual metaphor for database design, because you aren't just filing papers, you are laying down tracks.
Exactly. Just as those civil engineers in 1896 were physically digging trenches to dictate where the trains could and couldn't go, database designers use ER diagrams to route information.
We shift entirely away from the flat log.
Right. Instead of writing Charlie's at Kendall, we dig two separate trenches. We create an entity bucket called writer and another entity bucket called station. And the relationship that bridges them is just a verb. A writer visits a station.
And by drawing that map, Charlie's name only exists once in the entire database, securely in the writer bucket. The station's name only exists once in the station bucket.
So when Charlie taps his card, the system just links those two established facts together.
Exactly. But we do need to push the model a bit further, because Charlie isn't just some floating concept. He is interacting with physical hardware.
Right, he has a piece of plastic.
Yeah.
He has the actual Charlie card.
Which means our ER diagram has to mirror that mechanical reality too.
Ah.
The sources show the model evolving here. A writer doesn't just mysteriously visit a station. A card makes a swipe at a station.
Oh, okay.
The card is its own entity with a unique ID. The swipe is a specific event with a timestamp and a fare deduction. And the station is the physical location. We have to isolate all the moving parts.
Okay, here's where it gets really interesting for me. Drawing conceptual boxes and arrows makes total sense on a whiteboard. But eventually, this entire model has to be stored on physical hard drives, right? It's translated into zeros and ones.
Down to the metal, yeah.
So when I look at the fare amounts in the source, say a fare of 10, or maybe it's logged as $0.10, why does Squalite, the actual database engine, care so much about the specific data type? Like, why do we have to declare if that fare is text-t or an integer or a real number? To you and me, a 10 is a 10. Does it really matter to the machine?
Oh, it matters completely. It all comes
Definitely.
down to memory allocation and processing speed. The sources outline Squalite's 5 main storage classes. You have null, integer, real, text-t, and blob.
Okay, so real handles floating decimals, text-t is character strings, BLOB is binary data like an image.
Right, but the integer, the whole number, is where the mechanics are just brilliant. Squalite doesn't treat all integers equally. It dynamically allocates storage for an integer anywhere from 0 to 8 bytes, depending entirely on how big the number is.
Let's break that down mechanically for a second. A byte is just 8 binary bits, right? 8 zeros or ones.
Correct. And a single byte can represent a number up to 255. So if Charlie's fare is 10, under the hood, Squalite looks at the binary representation of 10, which is 2010.
Okay.
It sees that this easily fits into a single byte, so it caps it there. It only uses 1 byte of physical hard drive space. It doesn't blindly pad it with 7 extra bytes of empty zeros just to meet some arbitrary quota.
Oh, wow. But if they had to record a massive number like, I don't know, $1 billion MBTA budget figure.
And it would scale up. It would use the full 8 bytes.
So it's flexible, and when you multiply that dynamic scaling across millions of individual swipes every single day.
The savings in physical storage and retrieval speed are astronomical. If you improperly define that column as TextT and force the database to store the distinct characters 1 and 0 as a string for every single transaction, you bloat the system.
You'd slow down processing.
Exactly.
Yeah.
And massively increase the hardware costs to maintain the database. Strict typing optimizes physical reality.
But the sources also highlight something else. They mention that Squalite has a feature called type affinity, which groups data into these broader categories like Texas, numeric, integer, real, and blob. And type affinity actually makes Squalite surprisingly forgiving, right?
It does. It's a really unique feature.
So if you explicitly define a column to hold an integer, but some old glitchy card reader transmits the text string 10 like wrapped in quotation marks as a word, not a math value, SQLite won't automatically crash.
No, it attempts a silent conversion. It looks at the string 10, realizes it only contains numerical characters, and just intuitively converts it into a proper integer before saving it to the disk.
Okay, wait. Isn't silent conversion incredibly dangerous? If the whole point of database design is this strict, unbreakable structure, why do we want a system that starts quietly guessing our intent? What if it guesses wrong and corrupts the entire ledger?
That is a very valid concern. It is a calculated compromise. You have to remember, Squalid was designed to be embedded in everything. Cell phones, web browsers, IoT devices. It recognizes that raw data inputs from the physical world are frequently messy.
People build glitchy hardware.
Exactly. So its type affinity rules act as a built-in shock absorber. Now, it won't convert 10, spelled out with letters T-E-N, that will absolutely fail.
Really?
But it will salvage the string 10. It cleans up human error to preserve the structural integrity of the table.
So it's acting as a translator between chaotic human input and rigid machine logic. I love that. But even with relationships drawn, and even with every byte of data perfectly typed, a database without strict behavioral laws is still just, well, a bucket of numbers. To enforce reality, we need table constraints.
Yes, because without constraints, your perfectly typed integers don't actually mean anything. Constraints are the physical laws of the database universe.
The sources list several key ones: primary key, foreign key, check, default, not null, unique. I want to step away from the abstract code for a second and think about the physical infrastructure of the subway system to really understand these.
I think that's the best way to look at it.
So, not null. That isn't just a rule in the code. It is the physical turnstile. You walk up, and if you don't present a card with a value, the metal bar physically locks. You cannot leave the entry blank. No card, no entry.
Spot on. And following that infrastructure analogy, unique is an anti-passback mechanism. It ensures that someone isn't using, say, a cloned version of Charlie's card to enter a different station at the exact same time. The database demands that every active identity in the system is completely singular.
That makes perfect sense. Now, what about the cheat constraint? Because that feels like it handles internal logic, right?
Yeah, the cheat constraint evaluates a specific condition before allowing the data to be written. In transit terms, it might ensure that the fare deducted is always greater than 0.
Oh, right, because you don't want a system glitch allowing a negative swipe that actually, like, deposits money into a rider's account when they board a train.
Exactly. The database physically checks the math before opening the gate.
Now let's talk about the big ones, the primary key. The source material actually includes an image of the classic Charlie card design. It's got the green stripe, the cartoon illustration of the guy in the hat handing his ticket over.
It's iconic.
Oh.
And every single one of those physical plastic cards printed and distributed in the real world must map to a primary key in the digital world. The primary key uniquely identifies a specific row in the cards table.
It guarantees that Charlie's specific piece of plastic is mathematically distinct from Alice's piece of plastic.
Exactly. Their balances can never overwrite each other.
Okay, but earlier, we separated our data into isolated buckets. We have a swipe bucket and a station bucket. If they're totally separate, what stops a glitching card reader from logging a swipe at a station that burned down 50 years ago? Or, I don't know, a station that hasn't even been built yet? They seem too disconnected to catch that.
And if we connect this to the bigger picture, that is the exact vulnerability the foreign key is designed to solve. The foreign key acts as a physical track switch.
How so?
Well, when the swipe log tries to record that Charlie entered Park Street, the foreign key constraint pauses the transaction. It actively looks across the database over to the station's table and verifies that a primary key for Park Street actually currently exists.
Whoa. It cross-references reality.
It demands proof of existence. If the card reader malfunctions and tries to transmit a station ID of 999, and station 999 doesn't exist in the verified stations table, the foreign key just flat out rejects the swipe. It completely prevents the database from hallucinating a physical reality that isn't true.
That is just brilliant for maintaining law and order in the present moment. But, the physical world doesn't sit still. The sources provide this great visual of the modern MBTA rapid transit map, and it is a sprawling, intensely complex web.
Oh, yeah.
You have the red line stretching out to Alewife, the orange line to Forest Hills, the blue line, the green line branching off into 4 different directions, the silver line. I mean, it is a beast of modern infrastructure.
It is vastly different from that single dirt trench they were digging in 1896.
Exactly. So how does a database schema that was rigidly locked down with all these constraints to mirror the simple reality of 1896 adapt to the sprawling reality of today?
That is the true test of a database administrator, because databases are living entities. You cannot simply pull the plug, delete the entire MBTA database, and start from scratch every time a new train line opens.
Right, people lose their minds.
You'd instantly wipe out decades of financial audits, historical ridership data, and user balances. It would be chaos.
Okay.
So the schema has to evolve while the system is running.
And the sources dive into how we do this, right? Using the alter table command. So we don't destroy the house, we just renovate it.
Precisely. Under alter table, you have commands like add column. Let's say a century ago, civil engineers just didn't care about wheelchair accessibility. But today, the database absolutely needs to track which stations have elevators.
So how does the database handle adding that to records from 1920?
Well, when you execute an add column command for accessibility, SQL has to inject that new structural parameter across millions of existing historical rows without crashing. Mechanics-wise, it typically fills that new column in the old records with a default value or a nullo value.
Okay, so signaling that the data is unknown for past entries.
Exactly, but it makes the structural space available for all future entries.
Got it. And you can also use rename column to keep terminology up to date. But then there is the most destructive command they mention, drop table.
Yeah, drop table is terrifyingly powerful. It doesn't just clear the data out of the bucket, it obliterates the bucket itself. The structure is gone. If the city completely paves over an old streetcar network and abandons the physical infrastructure, the database administrator can use drop table to permanently wipe its structural existence from the digital map.
So what does this all actually mean for you, the listener? Like, why should you care about data types, foreign keys, and altering tables? It's because every single time you interact with modern society, you are navigating these invisible trenches.
Everywhere you go.
When you scan a loyalty card at the grocery store, when you tap your phone to pay for a coffee, or when you just check a transit app to see when the next bus is arriving, you are dropping real-world physical actions into an evolving digital schema. That data is being normalized, it's being compressed into dynamic bytes, and it's aggressively cross-examined by constraints to ensure it flawlessly mirrors reality.
We spend our lives interacting with these massive, invisible architectures, and they are desperately trying to digitize the physical world as efficiently as possible.
To quickly recap our journey today, we started with poor Charlie, trapped in the redundancy of a messy, flat data log. We fundamentally changed the shape of his world by drawing boundaries with entity relationship diagrams. We optimized the digital footprint of his journey by understanding the underlying binary mechanics of data types. We enforced the strict laws of physics on his identity using constraints like primary and foreign keys. And finally, we explored how that entire rigid structure is actively altered to accommodate an expanding modern city.
This raises an important question, though, and it's something I think is really worth pondering the next time you tap a card or scan an app.
Okay, let's hear it.
We just spent this entire time talking about how these database schemas are meticulously designed to enforce our current physical reality. The foreign keys and primary keys rely entirely on the absolute existence of physical stations, physical plastic cards, and physical turnstiles.
Right, they demand a physical touch point to log the data.
But what happens when the physical paradigm fundamentally shifts? Imagine if tomorrow's transit system completely abandons physical infrastructure. No more turnstiles, no more tapping cards.
Like it relies entirely on frictionless, stationless GPS tracking.
Exactly, where you simply walk onto a train and your phone silently calculates your exact distance traveled in real time.
Oh, wow. The current database structure would have no idea how to process a continuous spatial coordinate instead of a discrete swipe at a fixed station.
Precisely. So do incredibly structured, deeply constrained historical databases eventually become a prison? Do they actually make it harder for a society to innovate because the cost and danger of translating a totally new physical reality into a 100-year-old rigid digital schema is just too high? We build these systems to perfectly capture today, but in doing so, we might be locking ourselves out of tomorrow.
That is a staggering thought. Are the systems we architect today going to become the anchors that hold us back? As you go about your week, look at the physical touch points around you. Look at the cards in your wallet and the scanners at the store, and just wonder how adaptable the invisible blueprints beneath them truly are. Because they aren't built to evolve, our data might just end up like Charlie, unable to ever get off the train. Thanks for taking this deep dive with us.